Hey everyone, I'm Ghada Almashaqbeh from the University of Connecticut. Thanks for being here, where in this talk I'm gonna take you to a different land or different world where you will hear about concepts that you think you might know, like destructive measurements and unclonability. However, I will tell you about these in a different context, in particular about or in the context of unclonable polymers and their cryptographic applications. This is an interdisciplinary research effort that involved researchers from several fields and backgrounds, including cryptography, computational biology, and biochemistry. So let's get started. Imagine we have memory devices that are unclonable. Furthermore, once you retrieve the data stored in that memory device, this device will self-destruct. Moreover, if this device is storing several messages, you can retrieve only a few of them, but not all of them, after which the device will self-destruct. Such bounded query memory devices have several applications. Maybe the most notable one is bounded execution software. These are secret programs or programs with some secret state where you can execute them or run them over only a few distinct inputs rather than forever. It's well known that building bounded execution software in the classical model is impossible because simply digital data can be copied and yeah, and you can execute the program as many times as you want. And even maybe surprisingly, in the quantum model, bounded execution software is also impossible. So without these special memory gadgets, you cannot construct one-time or k-time quantum programs. So the use of one-time memory devices or these like bounded query memory gadgets, this idea was put forward by Goldwasser, Kalai, and Rothblum, who showed that you can combine garbled circuits with one-time memory devices to build one-time or k-time programs for any general functionality. These one-time memory devices, as you see here, a device will store two secrets, which are basically the labels of the wires in the garbled circuit. And the evaluator can retrieve only one of the secrets, but not the other. After that, the device will stop responding, which is basically it will self-destruct. This work didn't show like a concrete construction for these special memory gadgets. They just provided general directions that these memory gadgets can be constructed using trusted hardware by tamper-proofing a whole computation, while assuming that these sophisticated hardware tokens resist side-channel attacks and reverse engineering, which we know that are problematic and even can be broken. So we wondered if we can build bounded like data retrieval memory devices from a different hardness assumption or using a different technology. And to achieve that, we joined forces with top-notch biology researchers in order to find an alternative technology to build unclonable and self-destructive memory devices. We wanted to do that in a rigorous way by laying down foundational modeling and formal security proofs for these memory devices. And we developed, or we wanted to develop algorithms and cryptographic techniques to amplify the weak properties of these memory devices in order to build more sophisticated and provably secure cryptographic applications. Our quest was motivated by recent advances in DNA synthesis. At a high level, you can take any digital message and store it in the form of a DNA material. So you take that message, you encode it into a sequence of nucleotides, and then you synthesize the sequence to obtain the DNA material. Kenshak, don't focus on the biology details. Just keep in mind the high picture that, or the high level picture that you can take any digital message and store it in the form of DNA. However, DNA evolved to be clonable. So you can take the DNA sample and you can replicate it as many times as you want, meaning that you can replicate the data that is stored in that DNA as many times as you want. So at that point, we started looking for another biology polymer that we can use for our purposes. And we found out that proteins, similar to DNA, can be used to store digital data. The only difference here is that the digital message will be encoded into a sequence of amino acids, and that sequence will be synthesized to produce the protein material. And here the magic started. First of all, proteins are unclonable. The central dogma of molecular biology states that once information has got into a protein, it can't get out again. So, which means that if you have a sample of protein, you cannot get the genetic information that will allow you to clone that protein out of it. And here I am talking about proteins in small samples. Um, and this challenge has been standing or is still standing for many decades now, and even for a billion years of evolution. And to us cryptographers, this is just a biochemical one-way function. So it's easy to go in one direction, but it is hard to reverse that operation. And as cryptographers, we know what to do with hardness assumptions. We turn lemon into lemonade. The other feature of proteins is that sequencing the protein to get the information that is stored into it, which is the amino acid sequence that we can decode it into the digital message, is fully destructive. So this machinery, the mass spec, in order to synthesize or in order to sequence the protein for you, it will destroy the bonds in the or the chemical bonds in the sample, which means that the whole sample will be gone after doing the sequences, or the message retriever or the data reading in that protein. Also, this machinery either outputs the message or the protein sequence or nothing, and keep that point in mind. And in order to sequence a protein, you must provide this machinery with an enough amount that is highly purified, that will exceed the required threshold. So if you feed it with a random set of proteins, it will output nothing because the purity level is not met. So based on these observations, we developed a novel protocol to build what we call consumable memory tokens. So as before, you take the digital message and you synthesize it into the protein material. Let's call it the target protein. Then we connect this target protein with another shorter protein sequence that we call the header, such that this header is recognizable by a set of matching antibodies. The header to us is the secret key that is attached to the secret message or to the payload. And knowing the digital description of the header, which is its sequence that will allow you to synthesize that protein, will allow you to identify the matching antibodies. So this is basically the secret key that must be hidden. Then we mix this, which is the protein that represents our message, with a massive set of random proteins, each of which is attached to a random header, such that all these proteins have similar physical features, so it is not easy at all to distinguish them from each other. And the vial of the protein mix, as we see in the figure here, is the consumable memory token device that our protocol builds. To retrieve the data, remember that if you feed the vial, which contains a random or a mix of random proteins, to mass spec, it will not output anything. So the whole sample will be lost, including the message. So we must purify the sample first, and we do that by applying the antibodies that recognize the secret header or the secret key that is tied to our message. So these antibodies will pull down the target protein, so it purified the sample. Then we cleave the header and we feed the pure protein sample to to mass spec, and mass spec at that point will identify the amino acid sequence of the protein, which can be decoded to get our digital message back. Um, so after working on that protocol, we kind of like our goal, or while working on that protocol, our goal was to assume the minimum on the biology side to get like the weakest memory device that we can build, such that at the cryptography level, we can amplify the weak properties of these devices to get more sophisticated applications. And so we did that just because we wanted to come up with the simplest assumptions or the simplest hardest assumptions that we require in our protocol. So this produced the following model, and which you can see that it has like weak properties. So our tokens can store only a small number of short messages using short keys. So if you have a long message that you want to store it in the consumable token device, you have to divide it into smaller messages and then store each one in a separate vial, for example. Also, the only meaningful interaction is by applying antibodies. So there is no other way to retrieve or to make a data retrieval query to the token other than applying the antibodies. And this is like a property of the protocol. Also, due to the destructive sequencing procedure, each data retrieval attempt will consume part of the vial, and for this we call the token consumable tokens. And to be on the conservative side, we wanted to account for powerful adversaries that we don't know their capabilities. So, although the honest party, we know exactly what the machinery she owns, at what threshold she operates, and so on. So we can calibrate the amount of protein in the vial or the memory token to be enough for only one data retrieval query. We cannot assume the same for the adversary. The adversary might own more advanced machinery that can operate at lower thresholds and smaller protein quantities. So the same amount that is used by the honest party can be enough for up to n queries by this advanced adversary. So our token has this power gap where the adversary can do more and can make up to n data retrieval queries. And this is actually a very important point that impacted what applications we can build using our memory tokens. Also, our memory token has a non-negligible soundness error, gamma. So, and this is coming because of the biology, like physical features, where the adversary who doesn't even know the secret key, which is the secret header and the matching antibodies, may apply another set of antibodies or another key that is close enough to the correct key. So that like closeness will give the adversary a probability gamma that he might be able to retrieve the message, although this adversary is using the incorrect key. For this reason, we have this non-negligible soundness error with our consumable token. We also extended our protocol to build what we call partially retrievable memory. So now the vial or the token will store V messages instead of one. Each of these messages is tied to its distinct or to a different secret key. And even if you know the set of the keys, you cannot retrieve more than n messages. And this is, of course, for the adversary. The honest party will have to choose one of these messages by applying or by using the corresponding key. After that, or just like, yeah, the work on this project took us a long journey. And remember, I mentioned at the beginning that we wanted to do this work in a rigorous way by formalizing a model capturing the memory devices that we build, their security, some amplification techniques, and then advanced applications. So this Yeah, this journey was long, starting from the biology and understanding the capability that proteins have and what guarantees they can give us. We build what we call the vector-based model, which is like a mathematical representation of proteins and the biochemical experiments that happen in the wet lab. So we represent the vial as a vector of protein quantities, and we represent the biochemical procedures that happen in the wet lab as algorithms and operations operating on these tokens. Then we took that mathematical representation and we alleviated that and defined an ideal functionality for consumable tokens. And we showed that the vector-based model representation realizes this ideal functionality. And so we have like secure construction for consumable tokens. Then we developed several cryptographic and algorithmic amplification techniques to amplify the security guarantees and the weak properties of consumable tokens, and we showed several applications of these tokens. In the interest of time, I will talk briefly about these applications, just to give you a sense of the capabilities and how powerful the consumable memory tokens are. And towards the end, I will talk about the relation between the unclonability paradigm that we get from proteins or unclonable polymers and the one that we get from quantum, and whether consumable tokens will allow us to build like one-shot signatures and other unclonable cryptographic primitives, and maybe motivate you with some future work directions and see if you might be interested to work in these directions. So for the applications of consumable tokens that we show in our paper, we have two of them. We have digital lockers and one in time programs. So digital lockers are basically, you can think about it like an obfuscation of point functions, where this function will output nothing except for the point that is hard-coded in that function. So it will output a multi-bit message. Um, from the literature, we know how to build digital lockers with the guarantee that the only potential attack is brute search attacks. So just searching the space until you find the key, and then you will be able to retrieve the message. And in particular, the focus here is on like encryption with low entropy keys or passwords, like human generated password. So the goal is to find the password that will allow you to decrypt the message, which is the point that you hit when you inquiry the point function. And we wondered if we can build digital lockers that additionally resist brute search attacks. So although it's a password coming from a low entropy space, and the adversary definitely might be able to scan the whole password space, uh, still they cannot have more than few trials in order to decrypt the message or try or make password guesses. And yes, we showed that the consumable tokens can be definitely used to build this application. So the secret message that is supposed to be encrypted, it will be stored in the token, and the secret password that corresponds or that is tied to this message will be mapped to a token key, and that key is connected to the message, which is, yeah, in our protocol, it will be the header. So the adversary can try up to n passwords. Each trial will consume part of the token because it is a data retrieval query. And after n trials, the whole token will be gone. So there is no possibility that this attacker can do a brute search attack over the whole password space. The other application is one in time programs. This is a variation or a relaxation of the known one or k time programs from the literature. And we build that from our consumable tokens. And because of the power gap that we have between the honest party and the adversary, we have this variation. So again, this is a secret program or a program with some secret state. The honest party can evaluate that program over one input, while the adversary can evaluate it or execute it over up to n distinct inputs. At a high level, the idea is as follows. You take the program and you obfuscate it. And yeah, obfuscation is a strong assumption, but we show how to use IO in our paper instead of VBB obfuscation. And the program is modified before being obfuscated to do the following. In order to execute f over the input x, the evaluator must provide a secret message that corresponds, or secret string that corresponds to x. So the program first will check that, yeah, you have the secret message that corresponds to this x. If it is valid, that program will output f of x. And we store these secret messages in the token. And this will force the evaluator in order to query the program over any input to query the consumable token first with the key that corresponds to that input in order to get the corresponding secret message. And without that secret message, the program will not execute. So, and naturally, because we have the consumable token that allows to for up to n data retrieval queries, the program can be executed over up to n distinct inputs, but not more. Okay, so some direction that I am interested in these days is to look at the relation between the unclonability that we get from polymers or proteins and what we get from quantum. And to ask the question whether these two paradigms are equivalent, so you can pick and choose which one to use, or they are equivalent, it means that they are alternatives, or whether they are like incomparable and can be combined with each other to obtain the best of both worlds, to obtain a stronger paradigm that will allow you to do anything basically that you want with respect to the field of unclonable cryptography. So to compare these paradigms together, in unclonable polymers, we don't have the concept of superposition. So the output of reading a state or a data retrieval query here for us in the unclonable polymer setting will either output the exact message that was stored or nothing. There is nothing in between. There is nothing like projections in different domains and dimensions, nothing like quantum. Also, there is nothing like gentle measurement that don't disturb the polymer state. Like you can sequence the protein and get the information or the message without destructing the protein, which is actually a good feature. So whenever you are doing a data retrieval query and you feed the protein sample to mass spec, that sample will be destroyed, whether you get an output or nothing. The downside for unclonable polymers, and in particular the construction that we are presenting, is having this power gap between the adversary and the honest party. In quantum, both of them are equal. You can, it's like whenever you do destructive measurement, the state will be gone. Both parties will have the same capabilities, but yeah, in the unclonable polymer model, the adversary can do more because we want to be conservative and account for unknown adversarial capabilities that could be out there. And then there is the million-dollar question, which is like the core topic of this conference, whether we can use unclonable polymers to build one-shot signatures. Some of the potential constructions here, just like generic one, take the one-in-time program application that I talked about and just obfuscate a program that is basically the signing algorithm and the secret key is hard-coded in that algorithm. And then put the secret messages that correspond to the inputs in a vial and send that to the evaluator. Or maybe we can use the same hash and sign paradigm using the chameleon hash function from the one-shot signature paper. The, kind of like, in that scenario, Alice will sign a hash of some message, send it to Bob, and she will also generate all the randomness that is needed to equivocate that hash to become a hash of a different message, which is through the chameleon hash function, and store this randomness in a consumable token. And now for Bob, whenever he wants to sign a new message, he must like query the token in order to get the randomness that will allow equivocation, the signed hash to become a signature over the new message. Um, so in both scenarios, unfortunately, we cannot get one-shot signatures because of the power gap that we have between the adversary and the honest party. Yes, the honest party will be able to query the token once, so she will be able to sign only one message, so it is one-shot signature. However, the adversary can sign up to n messages. So if you think about applications like quantum money, or let's say double spending resistant digital tokens, we cannot obtain that. The adversary can spend a token up to n times, not only once. And the question here is, okay, so how can we achieve that in the polymer-based setting? It's like two directions: either close the power gap between the adversary and the honest party by devising a stronger biology construction or model. So this is more on the biology side. Or maybe, I don't know, we have to be smarter and figure out a different construction on the biology side that will make these additional queries that the adversary gets unuseful. So whatever can be done in queries can be done using one query, and at that point we will have the honest party and the adversary of equal power limits, let's say. Okay, and what to do next? So what is the insights of talking about these two different paradigms? I really believe that there is a way to connect these two paradigms together, which is hybrid and cloning model, to obtain the best of these two paradigms. So on the one hand, quantum alone doesn't allow us to build bounded execution software because it needs these bounded data retrieval memory devices, and on the polymer side, proteins allow us to build these memory devices. So this is one of the first directions to connect these paradigms together. So obtaining the bounded execution from the polymers and the no power gap measurement and data retrieval from quantum, this might allow us to do better and even obtain more capabilities and expand on the primitives that we already know under the field of unclonable cryptography. And if you are interested in working on this direction, feel free to reach out. I'll be more than happy to discuss more. Thank you so much, and I am happy to take any questions. Thanks.